Thank you for your patience. We're sorry we had the projector crashed on the room next door. It wouldn't recognize any of our computers, and so we finally had to give up and move everything over to this next room. And we went ahead and had lunch on the way, so apologize for the issues there. Okay, so last we were here, we had gone in and we were using GitHub here. Sorry, the text is too small. I can't fix that, but right here is the Windows client. And when we had opened it up in Explorer, oh, go away. That's the thing that caught me last time. Anyway, so we open up and we find the directory this is in, and then we had installed Visual Studio, and so we have Visual Studio open up, and we open that solution file, right? You'd normally go up and you would say open, and then project or solution, and then you go ahead and open up from that directory the SLN file, and that opens up the solution. So over here, you're going to see that we have a set of these properties here, and then you have this solution explorer, and this lets you see what the various projects are in Worldwide Telescope. And if you notice the directories we talked about earlier when we were looking at GitHub, these are represented in the project. So we have this right here is our setup project. So after we have a successful build, this makes it so all you have to do is download one file and it installs everything you need. You know, all the hundreds and hundreds of files that are created by the build all get turned into just one setup file that can be distributed on the network. This is the final payload you're going to try to achieve. This also requires that you follow the instructions and download the installer projects extension for Visual Studio that lets you build those types of setups. Then we have that WWT core, and this is the part that has all those classes that help you out with things like time and coordinates and blend states and everything like that. And then right here is the Worldwide Telescope Explorer project, and this is where the desktop app part resides. The main project in all of this is called 3dwindow.cs, and this right here is where the rendering loop happens, where startup happens and stuff like that. It's one big, huge, humongous file. It's not necessarily great programming practice to have one file this big, but after we had all the history of the source control as it grew and grew and grew, refactoring it to a bunch of little files would make it difficult to follow all the changes and things like that. And so it's sort of it's become a little bit more of a beast than it should be. But we did some refactoring of it when we switched to open source, but mainly it's a hysteresis that it's as big as it is. But this is where a lot of the main work happens. So we're going to go ahead and open that file up, and you can see right here there's a visual editor for this. This is also the main window, but we can also right-click on this. Right-click on it and view the code for the window as well. So I'm going to go ahead and bring up the actual source code for it, which will be C#. And so this is and while it's called Earth 3D, is because this project originally started a very, very, very long time ago as a viewer for TerraServer back in 2000, and eventually evolved into the taking over the whole universe and sky as well as Earth. But so the project goes back a very long time. One of the things we're going to do right here is just start off with running this. So to go ahead and run this project, we can go ahead and right-click on the project and just click Build. Okay, and I'm going to click a Rebuild here just to show you what to expect. And what this will do is it will build itself and any dependent projects necessary to debug. So now we have a runnable project. And we'll go ahead and start that up and click Start. And this is going to run it in debug mode so that we can set breakpoints and examine code. And now we're going to go ahead and see this. It will pop up a Worldwide Telescope initialization dialog here. And then...
What OS are you running? 8.1?
So right now, someone asked what operating system I'm running, and I'm running Windows 8.1 on this machine right now.
Try it under Windows 10? Because I just did it next door, and you get some errors in the build. You can make it run, but it doesn't build.
It runs perfectly fine in Windows 10.
The build doesn't build. I just did it.
Okay, so
John, this is Doug from Cambridge. Just a question. In the README file on the in GitHub, it mentions for if you're trying to build the distribution, you have to have a data file. There's a separate file on GitHub or broken up. Is the file? Do you want to go over how to do that?
sure. So so far we're just building it to debug right now. Okay, I will be going over that, but that's later on. So when we get to building the setup, we're going to go ahead and show you that. Okay, so at this point in time, as you can see, we're in the solar system mode, and we're able to move around. So we've built the code down. So now, essentially, the universe is ours to modify. So one of the things I'd like to do to make this as realistic as possible is, let's say, is there somebody out there who has maybe some simple visual change that we can make to Worldwide Telescope to actually edit the code and make it do something a little bit different that someone wants to throw out, maybe from the Cambridge side of things?
We're conferring.
Mark, do you want to change your name?
We're still thinking.
Let's say you want to change the name of a planet.
That's just data.
Okay.
We want Pluto to be bigger so we can be a planet.
Okay, we
or,
want to.
or adding a moon and Pluto. Add a moon and Pluto. Is that too much work?
Well, that would also be just data files as well. So some of these things are actually all achievable through data, and you don't really need to be able to have access to the source code to do that. And partly, I guess, partially, I could actually take questions for a half hour and keep giving that answer, because one of the cool things about WWT is it's so data-driven that you can change a lot of things just by editing the data. But there is let's go ahead and go to Pluto. Okay, so we're going to go ahead and fly to Pluto here, and we're going to mess with Pluto. As someone mentioned, make it bigger. They're actually the main planetary systems. I mean, the main planets and this dwarf planet that are in our system are actually run a little less data-driven. The moons are all data-driven, but the planets themselves have very high precision computation and a lot of special features and things like that. So we actually do render them in code. So I'm going to show you one of the things that's called edit and continue. It may not work entirely for this case, but one of the things that we can do is go ahead and bring in something called planets.cs. And this is where the planets are actually rendered. So we have things like enumerations. If you wanted to change the name of Pluto, you know, you could change the name of Pluto there. Now, it might break lots of other things because there's a lot of data-driven stuff that would mean that Pluto might not have its surface map. It, you know, might do a lot of really nasty things. So this probably isn't exactly, you know, one thing you want to do. But up in here is a lot of. I'm going to go ahead and increase the text size for you guys. Is that readable there? Is that readable in Cambridge?
Yeah.
Are you there?
That's good now.
Okay, you can read it in Cambridge. So I'm going to go ahead and scroll down here. Pardon me for a second here. We have some gravitational constants there. And so there are some tables here inside that define the geometries of the planet as we render them. Okay? This right here lets us get localized planet names. So this might be some place that we could actually translate it by actually putting names in the table. And all that does is affect the display name, but not actually the name that it's used to compare against data. So this might be a way that you could rename Pluto to something else and not break everything. Here we have planet angles and things like that. So all of the data on the planets and their rotations, rotation rate, the prime meridian, and everything like that is all set up here. So this is how we get all our times. Then we have over here the planet diameters. Okay. So one of the things we want to do is figure out which is Pluto. So I think this is like Sun. So if we look at that enumeration that we had earlier up here, let's go ahead and make the text bigger again. Okay, so that's 0, 1, 2, 3, 4, 5, 6, 7, 8. So it's the 8th item in the table, and what we want to do here is make give Pluto a serious, like, I don't know, 3 orders of magnitude bigger. Okay, so we're going to go ahead and stop the code, and then we're going to take away some zeros here, and then well, there's 2 orders of magnitude, and we're going to go ahead and restart. So given that this is something that's initialized pretty early on, I guess I could have modified it in place without changing the code by actually modifying the variable on the fly, and it would have suddenly rendered it a lot bigger. Maybe I could have shown you by modifying the data, but here I'm actually going to modify code, since that's the whole point of this. And now we're going to come in here and initialize things. And so we'll be in the solar system mode, and go ahead and dispatch that. And so here we are, and we're going to supersize things. Oh, well, let's fly to Pluto here. And if you notice now, Pluto used to only take a little tiny spot in our screen, and now it is. If we were to go in the supersize mode, which will still, we can see now that here is Pluto, and there's the other planets, and Pluto is now bigger than Jupiter relative to the other planets. So that's a tiny change that we just made by modifying code. One of the things that I think would be interesting is to look at, like, we have this new map that we put into Pluto, and so what I'm going to do is, given that we lost a lot of time with the whole technical issues, I'm going to walk through this one scenario end to end to show you how the pipeline works for rendering, and how we go about getting data from the server onto the screen. So I'm going to pull up some directories and structures that you guys will care about as developers or hackers on WWT. So first of all, there's a directory where we keep all our cache files, and it's users and then your username, and then it's appdata/local/Microsoft Worldwide Telescope. I know that's hard to see, but then you have directories under here which include things like communities, data, DEM, which is digital elevation maps, imagery, temp, and thumbnails. If we click on thumbnails, you'll see these are the thumbnails we've loaded so far that were unique. If we come in here and we start browsing like panoramas here and look at Apollo, and then we go around in Phoenix, you'll notice that as we those panoramas that we just looked at are now showing up here under the thumbnails cache. Okay, so everything we do in Worldwide Telescope, when we go out and get data over the network, in order to make it faster, the next time we can just pull it right out of the cache. Here is the imagery cache, and so these things have completely numeric numbers that are just hashes of the they're a numerical hash of the URL where the image is sourced from. And so that is a relatively low collision rate, so you basically should never have two of them that hit each other. There's like a 1 in so many billion chance that they will collide. We can go ahead and drill into any one of these directories, and you can see that they have subdirectories with levels in them, and then subdirectories with rows within that level, and then we can actually look at the actual image. And so here we'll do it extra large, and so you can see that's an image there. That's part of a data set that we looked at. This is one that has 2 levels deep, but that's the image that's shown in. So each of these, as we go deeper and deeper, it creates deeper and deeper directories for the tiles. So how does it go about finding where to get those tiles on the internet? So let's go ahead and look at the data directory. And what you'll find here is we'll see that there are some files here like we have clouds that are cloud maps. We have constellation name positions. We have constellation names with RA and DEC. We have some other different constellations for pictures. And we have all sorts of other files. But one of the things you'll see is explore root. And I'll go ahead and drag this and pop it into an editor. And this right here is a WTML file that's describing the image set data that we have for the Explore tab. So if you look here in the Explorer, you see there's Solar System, All Sky Survey, Spitzer, Chandra, Hubble, Astrophoto, Radio Studies, etc. So you have all of these. Where did these guys all come from? Well, right here is the Explorer root, and we have collections, constellations, solar systems, all sky surveys, Spitzer studies, and look at it. There's all of these folders and their icons that show up in that Explorer view. So this is the data that drives that Explorer tab in Worldwide Telescope. If we want to load up any of these others, we can go ahead and grab any of that data and go ahead and navigate into that. So we could actually load that URL up into a browser and download that file. So what I'm going to do is drill in a little bit more. So there's this thing called WTML cache, and that is going to have all of those the files that people open up for WTML files in Worldwide Telescope. Those are going to be cached in this directory. There's also another feature in Worldwide Telescope right here where you say look at, and you can say like sky, and then you have all these selections that are part of your drop downs. These all come from the base image sets, and if you look in that directory again for data, you'll see that there is image sets.wtml here, image sets 5, and then a language hash code so that you can have various different translations in different languages of those. And what we're going to do is go ahead and drag that and drop it into Visual Studio, and we can open that up. And this actually, now you can see what an image set looks like in Worldwide Telescope. So here is the base image set for Earth. I'll go ahead and pull one out. Well, let's start with Earth one here. So it uses XML description, and it starts with an image set, and then we have different parameters. It's saying that it's not a generic image set. Generic image set would mean that you say you have a tour or something that you want to display Earth, and so you just say, I want a generic Earth. I don't care what it is, but give me the Earth that's the default for this browser. And so then, instead of specifically having the metadata for where to find that map, it would just use any old Earth map that's the default map for the system. It tells you what type of data set it is, what band it's in, what its human readable name should be, and then it tells URLs of where that map can be found. So in this case right here, we have this URL, and there's these little squiggly brackets here that it replaces the instances of those squirrely brackets with a particular address. So remember when we were talking about toast quad trees, you start out with a single tile. That single tile in a quad tree scheme might be named A, or nothing, say, just an empty nothing. And then there might be A, B, C, D for each of the 4 quad tree options. So one way of addressing a quad tree is to say A, and then the next lower levels are A, B, AC, or AD are the 4 children of A. And then what you do is you keep stacking that choice. So it could be 0, 1, 2, 3, and then you stack digits on top of each other. And that, so if you're making this quad tree choice, you have one item and you can choose 4 children of that one item. And then you pick that item, and that adds to the quad tree address. And then each subsequent pick, as you drill in further and further, deeper and deeper into that tile pyramid, stacks the address deeper and deeper. That's one way to create a quad tree. And Bing Maps and Google Earth and Google Maps use that style of quad tree. There's also another way, which is the first level is a level of 0 and an X and Y of 0 and 0. And that's the first tile in a pyramid that works that way. So the address of the one tile at the top of the pyramid that has the entire data set in one small tile, its address would be level 0, X0, Y0. And then for level 1, you would have X0, Y0, and then another one that's X0, Y1, Y1, X0, and then X1, Y1. And so as your tile set grows and grows, you get more and more tiles at that particular level. So obviously, the more levels deep you go, the more data you're going to have. Some of those tiles can be empty. What this does is the WTML image set describes how to create a URL that can find any level of this data. And when you walk down a quad tree, you always start with the top of the quad tree, and then you inquire about the children. The minute that you ask for a quad tree address and you get no children, then you know you're done and there's no more data anywhere down that path. And so what this allows you to do is it allows you to drill in as deep as there is data and know when there's not data. There are some hints about in the WTML about what the base levels are, how many levels deep it is. In this case, the Earth goes 20 levels deep, but not everywhere on Earth goes 20 levels deep, but there's no level that's 21 levels deep.
Hey, Jonathan,
Yes?
can you maybe restart your screen share? It froze. I've still been looking at one file while you were talking, so maybe if you restarted all the screen.
Can you see this? Hello?
We're waiting. Hold on.
Do you see Worldwide Telescope here?
Now we do, yeah.
Okay. Not sure what's happening with Google Hangouts, whether it's just stuck, but so what I'm going to do now is we're going to actually walk down the code that actually renders this view of the sky right here. Okay? And as you see, as I zoom in here, there's a few things that are going to happen. As I zoom in, we get higher and higher resolution. There are a few debugging tools that are useful for looking both debugging data import as well as figuring out what's going on, like while I was developing it. When you zoom in somewhere, as we're progressively loading each layer of the pyramid, we have to get the data that we don't have. So the first thing we do is we try to render the top level of the pyramid, and we say, is this visible? If the top level of the pyramid is not visible, then nothing's visible, there's no more work to do, and so we just skip it. If we do, if we can render the top level of the pyramid, then what we do is we go to each of the children of the pyramid and say, hey, are you substantial enough that you're worth rendering separately from your parents? And so if the children are not in view, or if they're too high a resolution and it's not worthwhile, then they say, no, let my parent do the work for me. And so the parent can draw itself as one tile, or it can draw any 1/4 of itself and let the child decide whether it needs to render. If a child decides that it's not even on the screen or not visible at all, the parent neither renders itself nor the child renders. So what this means is that as I walk down that quad tree and I check to see whether each of those children are actually intersecting the view of my screen, I can quickly decide which tiles I need to actually draw what's on the screen. When I come to a point where I know I want to draw a tile but there's no data for it, then I need to go get this data from somewhere, and it's going to take a while, but I need to draw now. So what we always do is we always get the data for the root child, the root tile first. And we always get that data, so we always have something to draw. If a child is not ready to draw, the parent takes over for them. When the child is ready, then the parent lets the child draw, and so we only are we're never going to draw all white or all black unless we have no data whatsoever. And so this makes it so if you've seen some zooming map programs, when you zoom, you'll see a whole bunch of black tiles, and then they'll fill in with data. A bunch of black tiles, or even worse, white tiles, and then they fill in with data. This, as you zoom in, you see that it just gets sharper, but you don't see any like flashing or gaps or anything like that that's going on. But what's going on in the background is we're actually downloading. So what I've got loading here is this is the download queue, and when I move over, you're going to see that it fills up with a number of tiles that are our background. And what happens is it will have so many slots that it can download at any given time, and it votes for the most important ones, and they get downloaded first, and everything else waits. The minute that something goes off the screen, it stops getting votes. And so if we have something in the queue and then suddenly we're not looking at it anymore, we won't bother to waste time downloading it. And so this prevents us from wasting a lot of time of stuff that's already gone off the screen. So now that download queue is, if we're moving here, I'm going to go ahead and double click quickly. And what I just did there is this URL is a embodied URL with the parameters, and so it's hard to see right here for those people remote. It says dss.axp q equals 7, 78, 92, and that means it's level 7, and the X and Y address are 78 and 92. And so what it did is it took a theoretical unformatted URL that had placeholders in it, and it replaced them with actually materialized parameters for it that it needed to download it, and then it requested that from the server. And this is a single chunk of what we downloaded. This chunk on its own is not very useful. We need to render it as part of the entire sky. So now that we've sort of set up a little bit of the background, we're going to actually walk through the code that does that. And so I'm going to go ahead and click in here, and we're going to find go ahead and find the this function called draw tiled sphere. And this draw tiled sphere is the main function that draws all the planet surfaces, all the sky surfaces, and things like that that are all image based. And so what I'm going to do here quickly is right click on it and go to definition. Pardon me here, I'm going to make it so it's readable. So right now I'm right clicking here and I click on go to definition, and so now we have this function here, and I'm going to go ahead and set a breakpoint. And so what's happened here is the code was executing, I set a breakpoint, we're stopped, and we're now looking at the call for that function. So what were we drawing? If I hover over the image set, we're drawing the digitized sky survey. Unfortunately, you may not be able to see that on the other side as well, but that's what it says right here in this text. And it's drawing it with an opacity of 1 and with a color of white, which means that it's not tinted or anything. As we step through this code, I'm going to go ahead and step over some, and it's going to check out how many levels it needs to do. So it's 1 level high and 1 level wide, which is basically a single base tile. And then it's going to walk through and do some, some code on here. I'm going to go ahead and run it all the way down to step through here. So I'm going to go ahead and click Run to Cursor. Pardon me here. Going to go ahead and step through here. Okay, so this right here is code that's setting up a high dynamic range rendering shader. And for those of you who haven't seen that feature, I'll show you in just a second. But we're going to go ahead and click through that, and then right here it's going to walk through, and it's going to call the tile cache, and right here it's going to call get tile. And so what this is going to do is it's going to say, hey, is this tile in our cache? Do I have something that's already materialized that is viewable, that can draw itself? And that's the first stage. If you don't have any tiles, there's nothing to draw. It's just going to go away and do nothing. But if it returns a tile, and the tile is not null, and the tile is in the view frustum, right, which means it's visible, then we're going to draw it. And so as I step in, it's going to call that function on the tile class. It's going to say draw yourself, and all the things that act like images and catalogs in Worldwide Telescope that have this multi-resolution effect all derive from the tile class. There are different embodiments of that class for toast tiles, for Mercator tiles, and other things like that. So here we're stepping into this, and it's looking at doing things like checking its current render generation, and doing some other housekeeping chores, checking to see whether it's an error or not. I'm going to go ahead and make that larger again. And so if it's not ready to render, then it's going to go through initialize itself if it can. But in this case, I'm sure it's ready to render. And then so this is going to actually step through and it's going to step through and go ahead and call each individual child of itself and render. And so right now it's going to step through 2 children in X and 2 children in Y, and it's going to do the sets of checks where it's actually going to go into the tile cache and see if the child is available, and then if the child is in the view frustum, then it's going to attempt to draw it, if the child is big enough. And so as we mentioned earlier, this is the check where it checks to see whether it's large enough. And then if it's, it sets certain bits so that if the child can draw itself, then the parent lets itself know that it's that it doesn't need to, right? So anytime a child volunteers to draw itself, or the child is not in view, the parent basically is going to ignore that part of itself and either relegate it to the child or do nothing with it, because it's either relevant to the child or it's not visible to anybody. So this function continues through until we finally actually call the rendering code to draw the pixels to the screen. So this is lets you see that we've brought the code in, and we can actually step through this and sort of look at a little bit of what goes on in rendering. I hope this wasn't too complex of a sample to get your feet wet, but it gives you a little bit of the idea of how these tile pyramids work and what they do. So I'm going to end for now on this and hand it over to Ron, since we're quite a bit behind with the technical issues. But I'll take any questions before we're done.
Thanks.
Any questions? No, I think that's probably.
Miguel.
What I see, the code looks quite easy to create layers, and you show, like, I mentioned to you the idea of showing the galaxies in 3D by using different layers. It looks like just another loop there, right?
Yeah, so layers, Miguel asked the question, it looks pretty easy to add layers. And so that's correct, is that you can layer both different types of images by creating new layers that have another image set, and they're alpha blended together on final output. So you can have a foreground layer, a background layer, and opacity of how you draw a layer. You can also have layers that are sparse layers that only show one particular part of the sky, and then the rest of it they're transparent. I promised you a feature. You guys saw that code that was setting up for HDR rendering? Okay. If I take the Shift and Control key, or is it Shift Alt Control, and I move the cursor around up and down like this, I can actually change the contrast and brightness of the all-sky imagery that I'm working with. And so let's say I take a hydrogen alpha study. Let's see, where's the hydrogen alpha full sky? And so by holding Shift Control Alt and then moving my mouse over, I can change the dynamic range like this. And so this is showing how we plugged in a shader into the mix here, and it allowed us to do pretty cool stuff with how we handle the imagery. So how many of you who have been using Worldwide Telescope for a long time did not know that existed?
Everybody's hands.
That's everyone.
What's that? No one knew this existed?
Nope.
Apparently not.
Shift Control Alt. I think I built this feature for David Hogg and one of the Albertos or something that from Harvard. is it Alberto Pepe or something? Anyway, this is like a hack day feature at the American Astronomical Society meeting in Long Beach, like 3 years ago or something. Yeah, so this has been here for a while. But okay, well, I'm gonna have to log off this computer for a second for Ron to take over. Hopefully the projector will come back up. But we're going to take a couple of minutes here just for Ron to set up, and then he'll start on his presentation. Thanks for your patience through all the technical issues.
Hey, Jonathan, I think there might be a quick question.
Okay, sure.
And just now that I've messed up my display with playing with the HDR, is there a way to set it back to default?
Just do Shift, Control, Alt, and click on the center pixel of your screen.
He's counting.
Yeah, you can also turn the reticle crosshairs on, and I think that's the center reference pixel. So, or you can restart Worldwide Telescope.
Thanks.
And if you have a problem with that, you can just check out the code and do another pull request.
I knew he was going to say that.
Okay. Any other questions?
And this document, we don't have a listing of the keyboard shortcuts. This falls into that category anyplace. I mean, I have some and some of the other pieces of documentation. Maybe this is a reference might be good to
Maybe file.
I think there are a lot of these that are referenced in various forms online and in our user guides and stuff like that in the help files. We probably should go through to make sure that walk through the code and look at all the keystrokes that we're implementing and make sure that they're all well documented.
Well, creating like a cheat sheet, a ref card for Worldwide Telescope might be a good,
Oh, that'd be cool. Write a little PDF people can print out for a quick reference card.
Exactly. You want to file
Okay.
it, at least we don't forget.
Okay, well, I'm going to leave the call for a second and then switch on off to Ron here, who will be talking about the web control. So.
Okay, thanks.